All right, the stage is yours.
Thank you. Hello, everyone. My name is Sergey, and today with my colleague Alexander, we will present some details of our research of a popular cellular modem. Here is a brief overview of what we will be talking about. We will start with an introduction and then take a high-level look at what the modem is about, as well as review previous research we have been able to find on this matter. My colleague Alexander is a principal security researcher at Kaspersky SCS. He has extensive experience in reverse engineering of hardware, embedded and system software, professional background in cryptography, and he's also been sharing expertise with students as a senior lecturer. As for me, I'm also a security researcher and software developer with over 20 years of overall experience. Apart from doing the same technical stuff, I enjoy playing musical instruments and singing. The widespread use of cellular modems in products ranging from cars to medical equipment motivated us to do this research. The modems we will be talking about today have been identified to be used in at least the devices shown on the slide. And you can see they include industrial computers, medical equipment, laptop expansion cards, payment terminals, and cars. You can probably imagine the range of consequences that a vulnerable modem would cause if it was compromised. Before initiating the research, we searched the internet for any known vulnerabilities affecting the modem, but everything we could find was a single CVE, which is displayed on the current slide, which was a straightforward local directory traversal issue with very little impact, but it drew considerable attention from the media because they believed it might have serious implications for our safety. You might be wondering why is that, but picture a scenario where an attacker gains unauthorized access to a car's modem, allowing them to remotely control essential functions like braking or acceleration. Or in the medical field, a compromised modem could disrupt proper functioning of life-saving equipment, putting patients at risk. And modems used in payment terminals could enable financial fraud, industrial computers, and laptop extension cards could expose sensitive corporate data. That's why security assessment of such cellular modems is very important. We need to ensure that the vulnerabilities are identified by security researchers and mitigated before they fall into the wrong hands. Now let us examine the modem from a high-level perspective. Its software is comprised of 4 components. The firmware, which is the low-level code, including the operating system, application layer, which is tightly integrated with the low-level firmware, but it may include customized components tailored to specific customers' needs by the modem manufacturer. The remaining 2 components are Java remote control and the lightweight M2M agent, both implemented as Java midlets. Midlets are applications running on a Java virtual machine. The JRC and SLAE are so-called manufacturer midlets and possess manufacturer privileges. The JRC midlet is a part of the firmware package and is always updated together with the firmware because of its tight integration with the low-level code. This is also due to a massive portion of AT commands implemented in the JRC midlets code. All midlets are divided into the manufacturer and user domains. Midlets in user domain can either be signed or unsigned. Upon reviewing the manufacturer's documentation on the module, we learned it provides AT commands for various purposes, including commands for managing and listening of installed midlets and accessing and manipulating files on the internal flash file system. The first thing a security researcher would probably try is to read the contents of installed midlets. However, using these documented techniques, we were not able to find any midlet files on the file system. Further study of the documentation revealed that there are security mechanisms which prevent reading of JIR files from the file system. These mechanisms were implemented by the manufacturer to ensure confidentiality of midlets. The problem of ensuring their integrity might be solved using the digital signature feature, which is available for user midlets, but it is not activated by default. The confidentiality and integrity images, we were not able to find any update images for our modem on the public internet. In the following section, we will describe the firmware extraction process. The primary components of the module include Intel Xcode 625 baseband processor, a multi-chip package containing LPDDR and NAND memories, along with an RF transceiver and power amplifier chips. To extract the firmware image, we needed to desolder and read the NAND memory using a commercially available programmer. Since we now had a decapped module with its NAND memory chip removed, and we had no plans to restore it, in addition, we removed the baseband processor to check whether the JTAG pins are accessible on the back of the module. To do that, we relied on a BGA ball map for another Intel baseband processor found online, which happened to match the layout of our chip. After manually probing tiny 0.2 mm pads under the baseband processor, we managed to match the required JTAG pins with some pads on the back of the module, which were marked as do not use in the datasheet. To be able to connect to these pads, we had to design our own PCB where we had all the do not use pins routed to onboard connectors and test points. Due to the fact that all modem modules we had at our disposal were initially installed on end devices by a third-party manufacturer, we had to desolder them to mount them onto our PCB. Notably, the module datasheet contained a warning against attempting to reuse such already mounted modules in a different application, stating that an additional soldering cycle will likely destroy them. During our efforts, we have accidentally destroyed a few modules, but eventually we were able to get a few working PCBs where the modules survived. First of all, we tried to connect JTAG with available open source tools like OpenOCT, your JTAG, and others, but unfortunately, all we could get was the JTAG ID. Online sources suggested that the chip should contain an ARM 1176 core, but from what we observed, it was highly likely that there was an undocumented test access point in front of the ARM core, which needed some initialization sequence. We tried to fuzz the JTAG interface and observed some interesting effects after writing to certain JTAG registers, but we could not determine the necessary steps to fully activate JTAG. Since the Intel Xcode baseband was previously known as Infineon, we searched some technical manuals on older Infineon chips online, but unfortunately the information there was misleading and did not match our observations, so ultimately we had to abandon the JTAG road. After the short 20 minutes adventure into the world of JTAG, we now get back to the NAND flash. It turned out that there was no encryption or exclusive OR-based transformation applied to the data, so we started to analyze the image in more detail. In NAND flash, data is organized into blocks, and these blocks are subdivided into sectors. This flash memory is naturally prone to errors, so it incorporates error correction codes and supplementary data within a segment called the spare area. It also has a flash translation layer and a mapping table essential for translating of physical sectors into logical blocks. To ensure uniform wear of the data cells, data is sometimes transformed using a bitwise exclusive OR with a random sequence called gamma. In our case, there was no such transformation, and the spare area was located after every single sector. The sector size was determined to be 512 bytes. On the current slide, you can clearly see the sectors separated by 16 bytes of spare area data. To figure out how to reassemble the physical image into logical, we decided to solely look at the spare area. After isolating the spare area contents, the logical block number and logical sector number fields were clearly visible. Using this information, we now could reconstruct the logical blocks. So we crafted a simple script to reconstruct the logical blocks, revealing that only a few of them were actually populated with data. Notably, one block contained the firmware and app images, and another non-empty block included a FAT file system. After mounting the FAT file system, we confirmed that it is indeed the file system used to store midlets and other files. As mentioned before, while ordinary users can access it through specialized ET commands and Java are not visible through the standard interfaces. After a quick look at their contents, we found that the location where all the midlets are installed and moved on to analysis of their storage layout. Midlets are Java applications running on a Java Micro Edition virtual machine. On the Modem's file system, each midlet was represented by several files, including JIR file with the midlet code, JID file containing its manifest, and some other files whose contents was not clear yet. As we had mentioned earlier, the manufacturer has imposed restrictions on reading JIR files, and if you try to get a list of files in a directory of the flash file system using the IT commands, then any JIR files, even if they exist, will be skipped. It is also not possible to directly access them by specifying the full path. In addition, a midlet which was previously being copied to the flash file system will be copied to an unknown location upon installation, and the original file will be deleted. The file name of the original GIR file which was used to install the midlet will, however, be preserved and displayed when listing installed midlets, as can be seen on the screenshot. If someone tries to bypass the restriction on listing or reading GIR files by trying to access them from Java code of an own midlet, he will also face an error like the one you can see on the screenshot. As mentioned earlier, we found that each installed midlet is represented by several files. In total, there are 4 files. We will review their contents and function in the following slides. The file with .ss extension contains midlet permissions. Midlets can be granted either full or limited set of permissions based on the contents of this file. It is important that the digital signature of midlets is checked only during installation and not when the midlet is executed. The set of permissions shown on the screenshot corresponds to the manufacturer's security level. The .ii file contains service information, including the certificate used to sign the midlet and the native file system path to the JID and JIR files used when it was initially installed. The .ip file is basically the JID manifest. From the contents of this file, we can see that the midlet we are looking at is actually the GRC midlet, which is a part of the firmware package, as I mentioned earlier, because it implements a significant amount of AT commands in its Java code and extensively uses the Java native interface. You can also observe that the certificate store used to check the digital signature of this midlet is set to firmware. After finding such a hidden gem, we initially started reverse engineering of its Java code. We found a Java class which had a public static method accessible from any midlet, even not a previous one, which could be used to leak contents of all Java system properties, including the hidden storage root, which is the native path used to store installed midlets. Later, we found that the AT commands, which provide the FTP client functionality documented in the module's AT commands and reference, are implemented in the GRC midlets code. Privileged midlets, like the GRC midlets, have unrestricted access to the file system, including the ability to read or write GIR files and access hidden paths. Together with the previous vulnerability which leaks a secret file system location with the installed midlets, this gives an opportunity to read and write midlet files using FTP and elevate privileges of user midlets to manufacturer level by replacing the permissions description file of a user midlet after installation. Another vulnerability found in the virtual to native file system path conversion routine was a native path traversal vulnerability. It was due to the wrong order of checks made in the Java code. This way, we have found that in addition to the documented virtual root A, there exists an undocumented virtual root B, which is a subdirectory inside A. After successfully using FTP for downloading manufacturer midlets and escalating privileges of our test midlet to the manufacturer level, we made a fully local privilege escalation proof of concept, which does not require FTP. The thing is that to access files in the hidden folders, the access is not restricted if you know their names. The global restriction only applies to GAR files. So we crafted a midlet which elevates its own permissions to manufacturer level by finding its permissions description file in the hidden storage root and then overwriting it with a file which gives full permissions. And now we're going to demonstrate how it works. In the terminal on the left, we will execute AT commands, while in the terminal on the right, we'll monitor execution of our test midlet. First, we execute the AT-SJM command to install our custom midlet. After its installation, we execute commands to enable output of midlet execution logs to the terminal on the right. Then we execute another AT-SJM command to start our test midlet. During its first execution, the midlet searches for the permissions description file and replaces it with another high privileges permissions file, then exits, which is indicated by the message TalkMid exited. Then we again execute the AT-SJM command to start our midlet for the second time. And this time it initially starts doing the checks, but then it observes that it already has manufacturer permissions. To test the permissions, it tries to access and list the hidden folders in the virtual root of the user file system, then finishes execution. So, we have reviewed some of our high-level findings, which did not require reverse engineering of the modem's native firmware image. Now I will pass the microphone to my colleague Alexander, who will uncover the internals of the modem's operating system and its security. Thank you.
Okay, thanks, Sergey. And next, we will move on to the part where we'll discuss the features and threats of the modem's firmware. So, in our study of modem security, we identified two potential attack vectors. The AT command interface, accessible via physical access, and remote access via mobile network. And given that the attack surface is smaller for the AT interface compared to the mobile network, we focused our initial efforts on this area. We examined the security of the AT command interface by employing fuzzing techniques. So, to organize fuzzing, we need to create a fuzzer corpus and develop a method to receive feedback on the outcome of commands. The advantage of AT commands is their ease of access. Thanks to the manufacturer's documentation, we had information about typical AT commands supported by the modem and interfaces we could use to send them. In our case, we used the USB serial interface available on our PCB. Among the available AT commands, we discovered one that managed the output of logs of various levels, which was sufficient for governing feedback. Yet, with full access to the firmware image, we opted not to restrict our analysis to just the documented AT commands, and instead, of course, we thoroughly reviewed all AT commands available in the firmware image and divided them into two types, user and vendor. So, in Modem's firmware image, we identified a significant number of user commands, each defined by an informative textual label. These user-80 comments are efficiently organized within a data structure that links them to their associated operations: help, read, write, and execute. We counted over 300 such comments, although the user manual records less than 200, revealing a considerable number of hidden comments, even among the user comments. Additionally, the firmware did not include a comment that displays a list of custom-80 comments to user, as is sometimes found in products from other manufacturers. And besides 80 plus trace, we found an additional hidden gem, additional user hidden comment that was perfect for garnering feedback from our fuzzer. This comment provided information about all detected software and hardware faults on the modem. It also specifies the exact address at which a hardware fault occurred and shows the state of all registers during the fault. And this comment is available to all users, including those without any special privileges. Apart from a wide range of user-80 comments, we also encountered numerous vendor-specific ones. But these comments featured as distinctly different syntax similar to scripting language functions. To verify our hypothesis, we located complete scripts in the modem's firmware that were composed of these 80 comments. The comments themselves are namespaces containing various functions. And each namespace has its own descriptor outlining its purpose, version, and a reference to its supported functions. Many functions focus on testing different aspects of modem's hardware and only accept minimal user input that may affect some parameters of the testing itself, testing the signal level, testing the quality of communication channel, and etc. But not all of these namespaces turned out to be useless. In addition to the peripheral testing functions, several interesting namespaces were also discovered. For example, we found a namespace called sec. This rather self-explanatory name hid a whole set of functions for working with the modem and its firmware. This namespace contains functions that allow you to find out the IMEI of modem or may be refreshed. And when we decided to test them, everything was fine in the beginning. The function responsible for current settings of this namespace provided us with the relevant information, which you can see on this slide. But when we tried to call in more interesting functions, of course, when we are talking about sec namespace, we want to find out if we can maybe refresh modem or something like that. It returned only a runtime error. And we found out that many sensitive functions within this namespace turned out to require prior authorization, which involves a special key generated from the modem's hardware details like the serial number and IMEI. And this method is similar to the vendor unlock mechanism used in modern Android phones, where a special key is needed from the vendor to unlock the bootloader and flash custom firmware. Though we possessed the function code that validates this key, we opted not to generate the key ourselves, given the extensive range of other vendor namespaces and functions available for our exploration. For example, we found functions that clearly hint that their primary purpose is to read and write to RAM. Very nice, really. So, when we looked at their implementation, we easily confirmed this. Yes, exactly. The release version of the modem's firmware not only contains a command for obtaining a full trace in the event of hardware fault, but also a command for reading and writing memory. Very nice. Okay. But of course, however, despite the presence of such functions in firmware, it turned out that it was impossible to execute the code of these functions. And this time it wasn't due to limitations of a specific namespace. It turned out that all vendor-80 commands have certain access level requirements. And this level is global for the entire firmware and is set statically at the build stage. We haven't found a way to change it programmatically. In our case, this level not only did not allow us to call the memory read and write functions of specific namespace, but also made entire namespaces unavailable for calling. But unlike sec namespace, in this case, the check for call availability we decided to focus our finding to suitable vulnerabilities for this purpose. And using the information about all user and vendor IT comments, the parameters, purpose, we eventually assembled a small fuzzing stand. The stand is based on a regular Raspberry Pi, which sends the IT comments to the modem via USB, analyzes the response, and if necessary, hardware restarts the modem. We left the fuzzer to work for several weeks. And when we came back to check the logs, we found many software faults and a few stable hardware faults. After delving into details of the program code, we were able to find out that one of the AT command handlers uses a static buffer to store parameters passed to the AT command. The number of its parameters was limited, but their length wasn't. And therefore the user could cause a heap overflow with just one command with a significantly long input parameter. The type of parameters of this command is limited to numeric values only, so we decided not to check the possibility of obtaining code execution in this case, but to limit ourselves to denial of service. And the fuzzer didn't detect any other promising errors, so we decided to move on to analyzing the remote attack vectors via SMS messages and maybe find some right primitives there. Okay, and now we're going to talk about any SMS messages which modem can be executed. Okay, in total, the modem processes 3 types of SMS messages. Regular SMS messages, over-the-air provision messages for remote provisioning midlets, which we will talk about a little later, and finally, supple messages. And that's where we have discovered a remote code execution vulnerability. So, the modem offers a positioning feature using secure user plane location or supple subsystem. This subsystem is responsible for implementation of the supple specification, which implies exchange of special messages between home supple location platform and supple-enabled terminal or set. The modem itself is a terminal object according to the specification. Messages are exchanged using the user plane location binary protocol or ULP. And in this protocol, data is transmitted in the GSM network via push messages using web protocol stack. A typical ULP message is illustrated by the supple init message on this slide. The ULP protocol includes the ability to fragment the transmitted message, to allow the transmission of large binary messages via SMS at the push layer of VSP messages. On the terminal side, the VSP protocol provides indexing for fragmented SMS message transmission. The first supple message contains the total size of the message to be received, whereas subsequent messages contain data fragments to be concatenated. Example structure of the first SMS message is shown on this slide, and here we can see the next fragmented supple messages. There is VSP data only, whose overall size we have submitted earlier, and that's the point. During the analysis of the driver responsible for handling of ULP message fragmentation, we discovered a heap overflow vulnerability. Processing of web messages consists of copying of supple message fragments into a buffer whose size is equal to the size from the header of the first supple packet. But web protocol has its own variable to store data size. These variables are interrelated only in the part of web message reception algorithm. The sum of the sizes of all received web messages in a supple message must not exceed ULP size from packet. But the actual algorithm used doesn't check for it. Therefore, a received web packet will be unconditionally copied to a buffer with the size of not web but supple message. And this constitutes a classic heap overflow. Okay, we have heap overflow, but what can be done? Is it only a DOS or maybe something more interesting? The structure of the heap in which the overflow occurs is as simple as possible. The header of each chunk consists of a pointer to the next chunk and magic that indicates wherever the chunk is free or not, and that's all. the one-way list of chunks. So after crafting an appropriate SMS message, we managed to generate a heap overflow error from the first try, resulting in a hard fault and reboot of the modem. And we have a crash every single time in the same place. Heap malloc. A little chunk of free memory remains at the very beginning of the heap, suitable for our supple message. And the reason why hardware fault occurred was that during the overflow process we overwrote the pointer to the next chunk, which led to a data access exception, information about which we see in the logs with the help of at+xlog command we already mentioned. The R0 register contains the data controllable by us. So, if data in our SMS will not dummy bytes but the memory address, in such a case, what we will see in the logs is not just information about the exception, but also data from the addresses we specified. And at that point, we know nothing about internal modem's memory. We need something to read the memory and to understand how we can construct our remote code execution. So, as a result, we crafted a stand that provided us with the ability to slowly read modem's memory. And when I say slowly, while modern communication channels provide speeds of tens of megabytes or even gigabytes per second, our channel was able to provide us with about 7 bytes per minute. Therefore, it took several weeks to read all the memory we wanted to read. This speed was due to how the process of memory reading was organized. It consists of several steps. First, we caused an error on the modem side using the already known heap overflow method. But as data for the overflow, we used the memory addresses that needed to be read. Next, a hardware fault caused the modem to reboot, enabling us to subsequently find data from the requested address in the logs. And this process had to be repeated sequentially for all areas of memory that we need to develop proof of concept of our remote code execution. So, after an extensive period of gathering information about the internal structures, we could interact with following heap overflow, as well as, after analyzing the code of the memory manager, it became clear that the only way to ensure right data to an arbitrary address was to use the free function. The entire heap memory pool in which our supple message was located was shared between all processes of the modem operation system. The algorithm of the free function tries to allocate memory for some process that was blocked on the malloc function immediately after freeing. And this could be used to our advantage. To do this, it was necessary to create several additional structures in modem's memory using our heap overflow. So, using a fake thread structure in this way, we were able to ensure that a pointer to a buffer containing our data was written to an arbitrary address in the modem's memory. And of course, this data will be the code that needs to be executed, but more on that later. As a result, our sequence of actions for reading into modem memory came down to crafting several operation system structures in its memory. It was important that these structures are not overwritten during operation of the modem itself and that the overflow itself does not lead to a hardware fault. Therefore, by sending several supple SMS messages, we created our own valid section of heap chunks in memory, which was then integrated into the chain of chunks of the real heap. Instead of a real process, the free function tried to allocate memory for our non-existent process based on a fake thread structure, which we also saved inside one of our heap chunks. And finally, it's time for demo. Now the demo. Let me remind you that the write primitive itself should have allowed us to unlock access to the vendor AT commands for reading and written memory. So, on the left side, we can see all available AT namespace namespaces for any user. It's big, but these namespaces consists of functions for test only, except the sec namespace, which we talked about a time before. So what we want to unlock all other namespaces so we can do much more interesting things with the modem. To do so, on the right screen, we start to send in our supple SMS messages to get heap overflow and to use our write primitive to update our user access level. So we can access all AT namespaces. And after several seconds, we can see on the left side that after sending these supple SMS messages, we got much more AT common namespaces. And among them, we can find out that there are namespace for read and write RAM of the modem. And so we can, for example, read modem RAM with this unlocked AT namespace. Okay, we can read memory, but now we can not only read memory, but also write memory. Thus, we can easily bypass restrictions to this sec namespace, even without knowing the special secret key. Very, very nice. Okay, and so we already have the ability to write a pointer to our executable code in memory. All that remains is to find where to write it. There are many options for solving this problem, but the simplest and most stable one turned out to be to use the context manager, which in turn has a place where it dynamically executes code from memory. It's something like LPE in Modem's operation system. But execution inside the context manager imposes restrictions because our code has become part of critical section. It was necessary to find a way to rewrite a chunk of code in order to be able to fully execute the modem side. The memory containing the required section turned out to be mapped as read and execute, but further analysis revealed that it could be easily remapped as writable using our code executed by the context manager. And in addition, we've discovered that many physical memory pages were unmapped and not used by firmware, but could be used by us to store code and data. You just need to set an appropriate map for the memory management unit, and you can use much more RAM on the modem side. We already could execute our code inside the modem, and the last step remained for a full-fledged proof of concept was to install a custom Midlet to gain persistence. Of course, since we already knew the structure of the modem's file system, we could simply copy our Midlet file to it, but the vendor has its own legitimate way to install Midlets remotely and named over-there provision. To activate it, you need to execute a custom ET command. Then, using a special over-there provision SMS message, you can send commands to the modem to install, remove, or update Midlets. And that's exactly what we need. The entire process of over-there provision operation is controlled by the presence or absence of a single file with over-there provision settings on the modem's file system. If it's not there, then the modem will not respond to the such SMS. But if it exists, then all over-there provision capabilities become available to us. Therefore, we decided to activate over-there provision on the modem side as a proof of concept. So, as we said, for this we need to create a special file on its file system. But we need to somehow transfer the contents of this file to the modem via SMS. In other words, we need to set up our own communication channel with our executable code on the modem side. And this was done by injecting code directly into the process responsible for processing of SMS messages. For this purpose, we wrote our own small driver using ARM assembly to remotely interact with the modem's file system via SMS messages. We called it SMSFS, and build it into the structure of operation system file system drivers so that we can work with it at the operation system level. And thus, we were able to construct a stand demonstrating the possibility of a complete remote compromise of a modem, starting from the moment of sending the first sample SMS and ending with installing our own Midlet. Fully remote attack to completely compromise the modem. And that's it. On this, we get to the conclusion of our talk. As a conclusion, we want to highlight what makes it possible to proof of concept of exploit real remote code execution vulnerability in a such critical subject as modem. The main thing is that there is no cryptography for firmware security, which lead to easy firmware gaining and no cross-process restrictions. A DOS-like style is not a good idea from a security perspective, as we all know. And as a result, buffer overflow vulnerability from denial of service stands to remote code execution. And because this is a modem which used not only in a fast updated area like mobile phones, only telecommunication operator can truly help with the work in mitigation. And of course, to protect against those vulnerabilities, we also recommend to disabling of non-essential SMS message capabilities, enforcing rigorous digital signature verification for midlets and control of physical access to your devices, if it's possible, of course. All discovered vulnerabilities were reported to the vendor. In total, 2 critical vulnerabilities were found, a remote code execution vulnerability and a user Midlet privilege escalation vulnerability. In June, we are going to publish a full technical paper not only about those vulnerabilities we discussed today, but about modem internals too. So get in touch and feel free to contact us about this subject. Thank you for your attention. We'll be glad to answer your questions.
Right now there's time for questions. If you have any questions, you can either come here and ask directly, or I will repeat the questions for you. Any questions? I guess I have a question. So how exactly do you send the SMS in your test environment? Do you have like a local GSM, or do you have like real SIM cards, so you emulate the SMS sending?
In our test setup, we used our own 2G base station to send the test messages. And it's also good to note that in case of 2G, any device could be tricked into connecting to such base stations. So if it's in range, we could send to any device.
Anybody else questions? All right, then let's thank the speakers again.